So up here, I just wanted to show you an example of, this is actually from 12.6, but I want to show you what the whole idea is. So if I'm at a certain point, A, B, f of A, B, so like x, y, z, if I'm facing this direction, my slope is pretty flat, because I'm kind of like, here's the mountain here, and I'm on the side of the mountain, so of course if I walk this way, I'm not going up or down at all. It's pretty easy. If I turn, yeah. Now, of course, my slope is a lot larger, because now I'm going to, if I turn now, I'm like, oh shit. So now I'm going to walk up the mountain, or walk down the mountain. In both cases, my slope is a lot more than it is if I'm walking this way. Now, where would the slope be exactly 0, do you think?
At the top.
That's one place. Where else? And what direction would I face for the slope to be 0 for sure? Anywhere on that surface. I don't care where you are. Think about it. And what does the slope in this case mean? The change in what? Change in z, I love it. The change in my elevation, if you want to think of it again as a physical thing, as being on top of a mountain. The change in my elevation, the change in z as I change x and y. But again, see, it's the same problem I have with limits. How can you change x and y? You can go any which direction you want to change x and y now, right? In 2D, how can you change x? Or, you know, not a big deal. So here, I forgot where I was going with that. Shoot. Oh, so have we figured it out yet?
So if you set it equal to your z and make a contour curve, you could follow
Beautiful. I love it. If I am somewhere on the mountain, all I have to do is face in the direction of my contour curve. Because what's the contour curve mean? My z stays the same. So along the contour curves, or along the level curves, if you draw them in the xy plane, level curves, that's where the derivative, as long as you're facing in the direction the contour curve is going, the derivative will be 0, because you're not going up or down.
Because it's not changing.
It's not changing, exactly. So that's why, if you get in your head, when we talk about derivatives in 3D, we're talking about how does the output function, how does the output variable change as I change the input variables, which is the same as before, but we didn't have to say it like that, because we only had 2 little variables. It was always very clear what was the input, what was the output. Yep.
So in 2D you would say dy dx, in 3D you would say dz.
That's where we're going. Now 3D, now here's the problem with 3D. Since I am able to face any direction I want to now, I'm not stuck on a plane. I can now face up and down and left and right and all different directions in between. We have to first define what's the derivative of something in purely the x direction, parallel to the x-axis, and what's the derivative parallel to the y-axis. Because then what can we do once we have those defined? Can't we then put them together and make a little sort of directional derivative, like a derivative vector? Like, oh great, bring vectors back in. Thanks, Jeff. But do you guys kind of get what I'm saying? We have to create the building blocks of purely x direction, purely y direction. So if I want to go purely x direction, what do I do with my y variable? Hold it constant.
So partial derivative.
Exactly. We're building up. So anybody, if you've taken differential equations, I think some of you are in it or have taken it, you've already seen the idea of partial derivatives. Are they simple?
Yes.
Partial derivatives are simple. You've got it straight from a student's mouth, not from my mouth. The idea takes a little bit getting into, but all the derivative rules you know, they don't change. Thank God. So I wanted to kind of show you our motivation. We do eventually want to get here. This is 12.6. We eventually want to be able to write an expression for the derivative no matter which way I'm facing. But the only way to build that is to have my, like I hat and j hat, my x direction, my y direction. So that I can make little combinations of those. Yeah?
Are we skipping 12.4 and 12.5?
No. This is just a motivation for what 12.4 and 12.5 are trying to do. So don't get confused. 12.3 we're done with. I'm getting into 12.4. So let's say we have some function z equal f of x, y. And let me throw this up here just for reference. Here's the idea of what we're doing in 12.4. If we hold, this is our good old idea of h. Do you see this a plus h? So of course the blue line is the tangent line at that point in a way. If I hold y constant. So if I hold y constant at this b, my function actually becomes a function of z and x, not y is now held constant. So if I have a function z equals f of x, y, but I say y equals b, isn't this then effectively a function of x alone?
Yes.
So how do I take the derivative of that? I just, like always, take derivative. Ooh. Where whenever I see a y, I don't actually put b in. I just realize that I want to let y be a constant. Which constant? Any of them, because I want to be able to do it irregardless of what y is. So I want a function answer that I can plug in a value for y to specify which constant I wanted that y to stay at. Okay, so, for example, I don't think they've given me a formula, too bad for me. If we had the formula z equal, I think I have one that I wanted to do. Yes, cool. Like y equal to, I don't know, like y equal 3. So y equals 3. What does this become? It becomes that, right? And what's the derivative of that, of course? What's dz dx? I'm not introducing the new notation yet.
Minus 1/3.
6x minus 1/3. I love it. Okay, that's not amazing. So thankfully, we're not going to do that for every possible choice of y. There's so many freaking possible choices for y. So what we do is we don't replace y with anything. We just assume it could be replaced by a constant. It still is a variable, because what can you make that constant? Anything you want it to be. So to take this guy directly, I can't still use this symbol really here, because that kind of implies that I'm doing the entire derivative, the only way it can be done. So that's why we call it, we give it the name partial derivative. I'm not doing the total derivative. I'm only doing it in a certain direction. So the actual symbol we use, all it replaces is it makes it look a little bit cursive. Right? It makes it look like a delta symbol to me. But dz dx. Yeah.
And this is kind of like the concept of I hat and j hats, where it's just in the x direction and y direction.
Exactly. I don't want to go too far down the road because, well, eventually it will actually be exactly that. So I like the idea of creating building blocks by investigating how do I do just the x direction, parallel to the x-axis, parallel to the y-axis. And then we're going to say put those together to make any damn direction you want. So this is also known as, let me make this, so isn't this a function of x, y? You guys with me? So this is also known as the partial of f with respect to x, partial of the z in this case with respect to x. So you see both of these symbols used. So fy would be, what would I hold constant if I saw fy? You would hold x constant. Right? So here this is kind of telling you what variable you're assuming is the true variable. And the other one or ones are all constants. So here what would this be?
2yx minus 1/y.
I like it. So you take the derivative of x. This is just like 3x squared, same idea. That's a constant now. Minus 1/y. Cool. I like it. And so what would dz dy? What would fy be?
X squared minus x ln.
Don't integrate. Don't integrate.
Oh,
Differentiate.
X
So plus.
x y over.
You with me? Because the derivative of y to the negative 1 is negative y to the negative 2. So that becomes a plus over y squared now. You guys cool with that?
Yes.
Okay. So be real careful about going the wrong direction on your differentiation. Okay, and the funny thing is, we sort of have already done this. Doesn't this feel a little bit like when we did implicit differentiation a million years ago? Right?
Yeah.
Or maybe a little less.
Yeah. Kind of.
This sort of feels like implicit differentiation because it's basically what we did. If I had this, let's say it's equal to 0 for right now, just to keep this idea. How would you implicitly differentiate this? And we're going to do this a little bit further than we normally would. Go with me on this. Don't say I'm wrong, because I'm not. Nah. So you'd say 2xy x prime. Of course, we know x prime in this case would be 1. But so am I wrong putting it there? Certainly not. Because did you guys know you always do chain rule, right? You know that? Because what's the derivative of x squared? 2x times the derivative of x. Because the inside function is x. But what's the inside function derivative? 1. So the chain rule is always done. It's sort of mean that we teach it later. When we actually always do it, it only shows up when the inside function is not just x. Okay. So far I'm not really wrong. That's 1. Keep going for me.
That's 1. You are here.
Don't forget this now still. Right? The product rule here.
Oh,
Keep going.
China.
Oh, sorry.
X prime. Plus 1 over y squared y prime.
X over y squared y prime. I like it. You guys with me so far? Now notice something interesting. If you take out the x prime and collect those terms together, take out the y prime and collect those terms together. What's this and what's this? Those are your partial derivatives. So back when we taught implicit differentiation, if we really wanted to be evil or giving you a preview, we could have actually told you about partial derivatives. Because that's what that is. It's the partial derivative. So that's why it feels familiar, because you have basically done it. We just didn't call it that at that time. So, what do you think you would do, just looking ahead here, if I had w equals xy cubed z plus sine of zx minus last play. And then I ask you, what is dw dy? Partial of w with respect to what?
3x c y y squared
I like 3xy squared
plus
z
plus c.
is this, as far as y is concerned, this is constant. So do you see, I don't care how many letters I throw at you, partial derivatives are stupid easy. Stupid easy. Derivatives are stupid easy. Partial derivatives just say, focus on one variable at a time. Thank you, right? So much of this class is all about, well, you have to worry about all the freaking variables. Here, partial derivatives just say, just look at one at a time. So this would be, I could also write this as wy here, right? So what would wz be?
Plus cosine of dx.
You lost your son. Y
Times x. Z.
What comes out here?
X.
X, I like it. Yeah, here, why did I lose my sign? Because this is a constant if I'm, that's what this means, right? Y is the true variable. All the other letters I see are constants. That's what that means. Because it's hard for me to show this, of course, on a picture, because I've gone to the next freaking dimension up. But here, I am truly holding a constant. Now, which constant do I pick? Any I want to. So I still end up with a function of x and y and possibly, I still end up with a function with all my variables in there, possibly. Because I can make them any constant I want to. But that's why I only have to take a derivative of one variable at a time. That's why I call it a partial derivative. Yeah?
What happened to the sine 2x when you did dw dy?
according to y, if y is the only true variable, what is sine of zx? It is a constant, and the derivative of a constant is 0. Cool. You guys with me?
Mm-hmm.
So if my variable doesn't show up, that I'm taking the partial with respect to in a part of my expression, that part goes to 0. It's a constant. Sweet.
Remember these?
Oh, we got some. Let's see. Oh, cool. So the next level of this is how do I do? You know, levels. How do I do chain rule with this stuff? So, for example, I like that rash. Don't worry. Stay with me.
What the heck?
Chain rule scares me. It would be.
Yeah.
When you did the second one, you didn't treat sine 2x as a constant anymore?
Sine zx. Sorry, it's a little z.
Oh, that's
And now I'm doing the partial with respect to z.
ZX, I thought that was 2x. Okay.
Sorry, yeah.
Never mind.
So now that's why I stayed alive, because that is z in it.
So what do you want to?
So it's exactly the same idea as chain rule was before. And actually sort of related to what I was doing in the very beginning. What is the chain rule, basically? And I always hated it when it was written in general. But if I have, I like it. So if I have f of u, well, let's say f of u of t. Right, so effectively, it's the chain rule would be df du dt, and that's what df dt would be. With me? Now here's the really awesome thing about this. Let me see if we can do this without going through the whole proof. That's my hope. How many true? Let me see how I can say this. Isn't this like x maybe? So isn't it basically still just a two-dimensional thing in that case? So what do you think is going to change when I have more true variables in there? X is a function, is its own function of t, y is its own function of t. So I have x and y, not just x. I'm going to need this kind of thing for both of them. So I've just defined how to handle one of them at a time. I really just have to do both at once now. So what I'm saying is this. If I have, here we go. I have something like this here. The derivative of z with respect to t. I could do the chain rule with respect to x, and then the chain rule with respect to y. And we now know how to do that. We now know how to do one at a time. So we would do the partial of f with respect, with respect to x, dx dt, plus the partial of f with respect to y, dy dt. So incredibly enough, the more letters I throw in there, the more plus little thing, plus the little thing, plus the little thing I would put in there. So this I didn't need to do that for, and actually, we do this real quick. You just put an x in there, make it a little more directly obvious. I don't know if your teacher ever told you this. This isn't really necessarily true, but it happens often enough that I might as well make it. These kind of cross out so you get df dt. Right? Technically, it's not really what happens, but effectively that is what happens. So see here, both of these become df dt. But this is the part in the x piece, and this is the part in the y piece. So I need both of them to make the total derivative with respect to t. Do you guys get that? So this effectively cancels out. This effectively cancels out. I get two parts of the derivative of f with respect to t. When I put them together, I get the whole derivative with respect to t. Okay, good. So let's try an example real quick. Last thing we'll do. Oh yeah. Well, the one I got up there.
Yep.
Why don't we do the one on
Shouldn't
the
be.
What do you get that?
Yeah, the one I just said. Yeah.
Should be.
So dz dt.
It would equal X.
And you can put the little rule down. Let's put the little rule down. Dz dx dx dt plus dz dy dy dt. There's my little rule. And if you want to read the book goes to tree diagrams. And that's great if you like tree diagrams. I really don't see any reason for it personally, but if you like them, read through this section in the book. It might help you put together partial derivatives. What's dz d? Partial of z with respect to x. What's that? Yeah, I don't need that much. Y. Right? Because everything else is a constant according to x, right?
Partial
Right.
of x was y.
And dx dt. I don't know what dx dt is because they didn't tell us what it was, right? Plus, what's dz dy? Partial of z with respect to y.
Secant squared.
Secant squared, good. Dy dt. And if I now told you, oh yeah, x is sine t and y is cosine t, just to mix things around, you can finish that out, obviously, right? You can then throw in what those are. See, so the last step here would be, what's y? Cosine t. What's dx dt? Cosine t. Plus x is sine t. Here's a neat one. What's secant squared of y? Secant squared of cosine t, right? Because y is cosine t. Careful, you're thinking inverse. And what's dy dt? Negative sine t. Yeah. So it gives you a really nice framework to just throw things into the right place. Yeah.
Where did you get x equals sine t and y equals cosine t?
That has to be given to you.
Oh, okay.
It'll be given to you in some problems. Yeah.
Okay, it's given to us in the problem.
Exactly. Eventually, I gave it to you. All right. So just to make you realize, we did 12.4. We did a decent chunk of 12.5, to tell you honestly, right here. But there's some more stuff in 12.5 to go over. So we're not done with 12.5.